Good afternoon, all of you. In the previous class, we studied about Hess's law and thermochemical equations. And now we are moving on to the next topic, which is enthalpies for different type of reactions. So the first type of reaction which we will study the enthalpy for will be the combustion reaction. So the standard enthalpy of combustion. I hope you all are clear with what is a combustion reaction. So combustion reaction is nothing but a type of reaction in which a substance burns itself in presence of oxygen and gives us some products. So that's what combustion means. A substance burns itself, give out energy and give another product. So combustion reactions are always exothermic because they burn, and they are very important in industries like chemical industry, rocketry, etc. So this is the definition for standard enthalpy of combustion. It is the enthalpy change per mole of a substance when it undergoes combustion. So when a substance undergoes combustion and when it is in just 1 mole or unit volume of substance when it undergoes combustion or when it burns, so what is the amount of enthalpy involved in it? That is what the standard enthalpy of combustion means. And you know well about the standard state. So at standard state, per mole of that per mole is important here. If you see this definition closely, you can understand that it is nothing but the definition of standard enthalpy of reaction only. So standard enthalpy of reaction and standard enthalpy of combustion, there is a small difference, which is this. So per mole reactants whatever we take, for combustion we need just 1 mole of substance. If we are burning or if we are undergoing combustion for just 1 mole of substance, then we can tell it's a standard enthalpy of combustion. So all the reactants and products should be there in their standard states at specific temperature. So this we know because when we put this symbol, we know that it is in the standard state. Now we will see an example. So this is the combustion reaction of C4H10 or butane. This organic compound is called butane and it is nothing but our cooking gas itself. So it is a cooking gas combustion reaction given here. So butane combines with oxygen for the combustion and forms CO2 and H2O. So in this reaction, if you see, the C4H10 or the substance which we are actually burning is taken as 1 mole. And if you see here 13 by 2, it's not a usual fraction which we take. Then why we take this 13 by 2? So we are adjusting other all reactants. Whatever reactants are there in a combustion, we are adjusting that for 1 mole of the substance. Anyway, we can take just 1 mole of the butane. That is fixed. Then only it becomes a combustion reaction. So the reactant which we are actually doing the combustion, that we are taking 1 mole. And for that particular substance, we need to adjust the oxygen amount. So that's why we have taken 13 by 2. This 13 by 2 oxygen is the amount required for 1 mole of butane. That's why we have taken this type of fraction. So 1 mole of C4H10 reacts with 13 by 2 moles of oxygen, giving 4 moles of CO2 and 5 moles of H2O. In this reaction, the enthalpy of combustion at standard state is given as minus 2658 kilojoules per mole. That is the enthalpy which is being exchanged here. Now we will see another example. C6H12O6, nothing but the glucose. So glucose plus oxygen giving CO2 plus H2O. This is another combustion process. And the enthalpy of combustion here is minus 2802.0 kilojoules per mole. In both the cases, we have an exothermic reaction as it is showing negative sign. And one more fact is that this reaction also carried out in our human body. So it's a burning of glucose that also happens in our human body, but not as a real combustion. There is no much heat involved in our body as we know. So there is not the exact burning is happening, but we know that there are a lot of enzyme catalysis process happening in our body. So similarly, this C6H12O6 is break down into CO2 and H2O by different type of enzyme catalyst in our body. So the same reaction is happening but by many steps. So it is not actually burning, but it is break down into same products which we get in our human body. So that is an enzyme catalyst reaction carried out in our body, and the enthalpy change or enthalpy involved will be the same, because if it is done in one step or if it is done in multiple steps, we have studied that the enthalpy remains the same as it is a state function. So there will not be change for this, but this will be done in many steps. So next type of reaction is atomization, enthalpy of atomization. So with this word atomization, you can understand what is the process. So it is the formation of atom, atomizing something. We are atomizing something, and the enthalpy required for that atomizing is known as enthalpy of atomization. It is defined as the enthalpy change on breaking 1 mole of bond completely to obtain atoms in the gas phase. So we are breaking 1 mole of bond in molecule and converting it to atoms. So that's why we tell it's an atomization. Enthalpy change of breaking 1 mole of bond to get atoms in the gas phase, and that gas phase is very important here. So the example, H2 gas gives 2H gas and the enthalpy of atomization becomes 435.0 kilojoules per mole. And hydrogen molecule, 1 mole of hydrogen molecule is converted to 2 moles of hydrogen atoms. So molecule is converted to atom. That's why we tell atomization. And if you look closely, it is nothing but the bond breakage enthalpy only, right? So we have a hydrogen molecule like this and we are breaking the bond. So it is same as the bond enthalpy which we have studied earlier. So bond enthalpy is same as the enthalpy of atomization in this case, in diatomic molecule cases. So we just break the bond and split them into hydrogen atoms. And the enthalpy change is positive 435. So when it is a positive value, it's an endothermic reaction. It is accepting heat, or we are providing heat so that it will break. So in case of diatomic molecules, enthalpy of atomization is bond dissociation enthalpy only, as we told. So this is another example for enthalpy of atomization, where the methane becomes C plus 4 moles of hydrogen. So 1 mole of methane CH4 breaks its bond to form carbon gas and 4 moles of hydrogen. So in all of them, they are in the gaseous state, and enthalpy of atomization is 1665 kilojoules per mole. There also it is a positive value, hence it is an endothermic reaction. And it is not that of diatomic molecule, it is a polyatomic molecule. It is not just 2 atoms present. So in that case, it is not same as the bond dissociation, because bond dissociation tells us about breakage of a single bond, and here C is bonded with 4 hydrogens, and the shape of CH4 we will discuss in this class only. So each of the bond is breaking here. So it is not the bond dissociation enthalpy in this case, it is just the enthalpy of atomization, or enthalpy required to form atoms from the molecule, and that is endothermic too. And when we consider metals, they exist in metallic lattice. So when we see a reaction of metals, then the reaction is not similar to this. So here we can see sodium in the solid form is converted to sodium gaseous form. So in this place, the metal lattice is existing. It is actually in the metal lattice combined with the metallic force. They have combined in a lattice and they are existing like that. And when we provide a particular amount of heat, it will come out of the lattice, which is a solid form, and forms a gaseous atom. So here also the combined sodium atoms in a lattice is coming out as a single atom, which is sodium gaseous form. So here also the product is in the gaseous form, hence we can tell it's a enthalpy of atomization happening there, which is 108.4 kilojoules per mole. So when this particular energy is given to the lattice, the sodium metal, the solid, is getting transferred to sodium gas, which is in the atom form, which is in the isolated form, we can tell. And here the solid is getting converted to gaseous form. Yesterday we have studied what is the process of conversion of solid to gaseous form, which is sublimation. So in this case, the enthalpy of atomization is not same as that of bond enthalpy, but it is same as that of enthalpy of sublimation, which is represented by delta SUBH. That also you write in your notebook. Enthalpy of sublimation represented by delta SUB. Here SUB will come, SUBH at the standard state. So enthalpy of atomization is nothing but the amount of energy required to break a bond, break 1 mole of bond completely to form atoms in the gaseous phase. So that's what enthalpy of atomization is. And in case of metals, we are breaking 1 mole of bond from the metal lattice and making them free to the gaseous state, and we get an endothermic value. Next we will discuss more about the bond break or bond enthalpy. So as we know, energy is required to break the bond, but the same amount of energy is required or released when a bond is formed. That also we know. So for example, we have hydrogen molecule like this. So when we are breaking this bond and separating them into two different atoms, that requires energy. So we provide energy to the molecule or heat energy to the molecule and break the bond and form like this. But the same amount of energy which we use to break the bond is released from the atoms when they combine to form the molecule. So when they combine and when they break, the same amount of energy exchange is happening. So that particular energy is known as the bond enthalpy. So we have two terms here related to bond enthalpy, and we will be discussing or dealing more about the first kind of energy, which is energy required to break the bond. And we have two terms which are bond dissociation enthalpy and mean bond enthalpy. First, we will be discussing about bond dissociation enthalpy. The bond dissociation enthalpy is told for diatomic molecules. So this example we have seen earlier. 1 mole of hydrogen molecule is split into 2 moles of hydrogen atoms. There the bond is getting broken. H, the bond is getting broken and they are forming atoms, which is the 435 kilojoules per mole endothermic reaction is happening, and it was same energy or same process was happening in case of enthalpy of atomization. There also we mentioned that it is same as that of bond dissociation enthalpy. So defining bond dissociation enthalpy, it is the change in enthalpy when 1 mole of gaseous covalent bond is broken to form products in the gas phase. So gaseous covalent molecule is broken to form gaseous products, which is of atoms. And this type of reaction or this type of enthalpy is known as the bond dissociation enthalpy. In diatomic molecules, it is same as that of enthalpy of atomization. So in case of diatomic molecules, it is very simple. So we just need to find out how much is the enthalpy of breaking of bond and write it as a value. But in case of polyatomic molecules, there are a lot of type of molecules and lot of atoms involved. In that case, the bond breakage enthalpy of this particular bond will not be same as of this one. All those will have different type of bond dissociation enthalpies. So we can't tell one of them to be the bond dissociation enthalpy of this particular molecule. So as it is a polyatomic molecule, we have different set of finding. So in case of polyatomic molecules, bond dissociation enthalpy is different for different bonds within the molecules. So there, in case we take the example of methane, this also we have seen. So CH4 gives C plus 4H. Here the enthalpy of atomization was delta atomization is equal to 1665, and this is not the bond dissociation enthalpy at all. We can't consider this as the bond dissociation enthalpy. So how we will find it? So this is the methane molecule. When we break one bond out of this, it will become like this. So CH3, one positive charge will come, CH3 plus it will become. So the energy to break this bond will not be same as of this one. They are having same atoms, but once this bond is broken from an atmosphere where the carbon is having 3 hydrogens in it. So when we see just this bond, we can see carbon attached to 3 hydrogens. There the electronegativity factor, all that is different. But when that is removed first, and when we think about breaking this bond, this particular bond, then we can see carbon attached with 2 hydrogen and with this having 1 positive charge. So the atmosphere is changing. In this case, carbon with 3 hydrogen. In this case, it is 2 hydrogens, 1 carbon and a positive charge. So when the atmosphere changes, the bond dissociation enthalpy or the difficulty to break the bond will change. It might increase or it might decrease. So that's why each of them we are calculating. So CH4 giving CH3 plus hydrogen gas. It is the first reaction. So to break this particular one bond, we are writing the first equation. It will be around positive 427 kilojoules per mole. And next we are finding of the second CH3 giving CH2, which is 439. Again we are finding the next one. Each of the case we have different values. So we have different values for each of them. One is 427, one is 439, one is 452, one is 347. So we can't tell any of them to be the bond dissociation enthalpy of this particular molecule. So what we do? We take the mean of this, or we take average of this. So in polyatomic molecules, we sum them up and we get a particular value and we take the average of it. So that average is known as bond dissociation into mean, which is mean bond enthalpy. So in such cases, we have mean bond enthalpy, which we take the average of all the bond dissociation enthalpy. So the sum will be 1665. So 1665 divided by 4 will give the bond dissociation enthalpy or mean bond enthalpy of that particular molecule, which is methane. That's all about bond enthalpy. And one more fact is that when we have this bond enthalpy, we can actually find the reaction enthalpy or standard enthalpy of reaction from this particular values. So we can predict enthalpy of reaction in gas phase if we know the different bond enthalpies. So we tell gas phase because we have the enthalpy of breakage of bond in gas phase only. So when the reactants are in the gas phase, we can predict the enthalpy of reaction just by knowing the bond enthalpy. It is by the reaction delta RH or standard enthalpy of reaction is equal to sum of bond enthalpies of reactants minus sum of bond enthalpies of products. We have such kind of equation, but there we were substituting enthalpy of formation. So the standard enthalpy of reaction was equal to summation of standard enthalpy of formation, which is delta HF of reactants minus the standard enthalpy of formation of products. That reaction we know. But this reaction is used when we don't know the value of delta HF or the standard enthalpy of formation. When we don't know this particular value, we can actually use this equation. If we know just the bond enthalpies, we can substitute in this equation and find out what is the standard reaction enthalpy, which is delta RH. So this is an application of bond enthalpy. So with this we wind up our today's class. So we spoke about three concepts: study it well, prepare notes from the textbook and submit. Thank you.